Hello and welcome to Math Zone African Motives. Today, we're diving into a crucial differentiation technique known as the chain rule. The chain rule is the key to differentiating composite functions. That is, functions within other functions. Think of it like a set of nested boxes. To get to the center, you have to open each box one by one. By the end of this video, you will be able to apply the chain rule to solve differentiation problems, identify composite functions, and differentiate complex expressions step by step. So what is a composite function? It's simply a function of a function. Let's take an example. Consider e equals sine of x squared minus 1. This is a composite function. We have the sine function, and inside of it, the input is another function, x squared minus 1. Here, the outer function is the sine function, and the inner function is x squared minus 1. This nested structure is what we call a composite function, or a function of a function. Now let's explore the chain rule itself. It gives us a formula for finding the derivative of these composite functions. The rule states that if y is a function of u, and u is in turn a function of x, then the derivative of y with respect to x, dIBC, is equal to the derivative of y with respect to u, di or do, multiplied by the derivative of u with respect to x, do, dx. The most intuitive way to think about this is differentiate the outside, then differentiate the inside, and multiply them together. You take the derivative of the outer function with respect to the inner function, and then multiply that by the derivative of the inner function with respect to x. This rule can be extended to functions with multiple layers. For instance, if y depends on u depends on v, and v depends on x, the chain rule simply extends to a longer product. The derivative di/wash dx would be di do times do y do times dv. You just keep differentiating the layers and multiplying the results together. Let's formalize the step-by-step process using a method called u substitution. This method breaks the problem down into manageable parts. Step 1 is to identify the inner function and set it equal to u. Step 2 is to find the derivative of the outer function do and the derivative of the inner function do dis. Step 3 is to combine them using the chain rule formula. And finally, step 4, you replace u with its original expression in terms of x. This is crucial because our final answer must be in terms of x. Let's put this into practice with our first example. The problem is to differentiate y equals sine of x squared minus 1. This is a composite function, so we'll use the chain rule. Let's follow our 4 steps. First, we identify the inner function. The expression inside the parentheses, x squared minus 1, is our inner function. So we set it equal to x squared minus 1. By making this substitution, our original function simplifies to y equals sine of u. Next, step 2. We find the derivatives of y with respect to u and u with respect to x. For do dx, the derivative of x squared minus 1 is 2x. For do, the derivative of sine u is cosine u. Now for step 3, we substitute these into the chain rule formula, di/I dx equals di/do times do /c. This gives us dx equals cosine of u multiplied by 2x. Finally, step 4. We replace u with its original expression, x squared minus 1. So dx is 2x times cosine of x squared minus 1. This is our final answer, which we have verified matches the memo. While the substitution method is great for learning, with practice, you can often apply the chain rule without writing down u explicitly. This makes differentiation quicker. The logic is still the same. Differentiate the outer function, keeping the inner function intact, and then multiply by the derivative of the inner function. This shortcut, or direct application, is essentially combining our 4 steps into one. Let's revisit our first problem, y equals sine of x squared minus 1, to see it in action. First, we look at the outer function, which is the sine function. The derivative of sine of something is cosine of that same something. So we write down cosine of x squared minus 1. Next, we multiply this by the derivative of the inner function, x squared minus 1. The derivative of x squared minus 1 is 2x, so we multiply our result by 2x. This gives us 2x times cosine of x squared minus 1, the same answer we found with u substitution, but in fewer steps. With practice, you'll find this method very efficient. Let's try another example using the direct method to build your confidence. The question is to differentiate y equals sine of cosine x. Here, our outer function is sine, and our inner function is cosine x. We apply the outside-inside rule. First, the derivative of the outer function. The derivative of sine of something is cosine of that same something. So we differentiate sine while keeping the inner function cos x unchanged. This gives us cosine of cosine x. Now we multiply by the derivative of the inner function. The inner function is cosine x. The derivative of cosine x is negative sine x. So we multiply our previous result by negative sine x. Combining the two parts gives us our final answer. Dx equals negative sine x times cosine of cosine x. Again, this matches our memo. Let's tackle a slightly more complex example with multiple layers of functions. We need to differentiate y equals ln of sine of x squared. Notice there are three functions here: the natural logarithm, the sine function, and the polynomial x squared. We apply the chain rule from the outermost function inward, differentiating each layer in turn and multiplying the results. This is like a chain reaction. The process can be visualized as a series of nested operations. First, the derivative of the natural logarithm. The derivative of ln of something is 1 over that something. So we have 1 over sine of x squared. Next, we move to the next layer in, the sine function. The derivative of sine of something is cosine of that same something. So we multiply by cosine of x squared. Finally, we reach the innermost layer, x squared. The derivative of x squared is 2x. We multiply by 2x. Putting it all together, we get dx equals cosine of x squared over sine of x squared multiplied by 2x. Recognizing that cosine over sine is cotangent, we can simplify this to our final answer. Dx equals 2x cotangent of x squared, which is consistent with the memo. Let's explore an application of the chain rule involving exponential functions. The problem is to find the derivative of y equals e to the power of sine of x squared. This function also has three layers, the exponential, sine, and x squared. We'll follow the same procedure. Differentiate the outside, then the next layer in, then the final layer, and multiply everything together. Let's begin with the outermost function, e to the power of something. The derivative of e to the power of something is just e to the power of that same something. So we start with e to the power of sine of x squared. Now we move to the next inner function, sine of x squared. We already know how to differentiate this from our previous example. The derivative of sine of x squared is cosine of x squared, multiplied by 2x. Let's multiply this result with the derivative we found for the outermost function. This gives us dx equals e to the power of sine x squared times cosine of x squared times 2x. A quick rearrangement gives us the final answer. The final derivative is 2x times cosine x squared times e to the power of sine x squared. This result is verified against the provided solution. Let's work through another problem from the notes. Y equals ln of sine x. Here, the outer function is the natural logarithm, and the inner function is sine x. We apply the chain rule. First, we differentiate the outer function, ln of something. The derivative of len of sine x is 1 over sine x. Next, we differentiate the inner function, sine x. The derivative of sine x is cosine x. So we multiply our previous result by cosine x. This gives us dx equals cosine x over sine x. We can simplify this trigonometric expression. Cosine over sine is equal to cotangent. So the derivative of ln of sine x is simply cotangent x, which we verify against the memo. Now, let's explore differentiating logarithmic functions to bases other than e, using the chain rule and the base change law. The problem is to differentiate y equals log base x of 5. We can't differentiate a function with a variable base directly. We need to use the base change law to convert it into natural logarithms, or logarithms with a fixed base, like 10. The base change law states that log base b of a is equal to ln a divided by ln b. Applying this to our problem, we get that y equals ln of 5 divided by ln of x. Now, this looks like a job for the quotient rule. However, notice that the numerator, ln of 5, is a constant. We can rewrite the function as a constant times a function of x y equals ln of 5 times the quantity ln of x to the power of -1. This is much easier to differentiate. Now, this is a product of a constant and a composite function. The derivative is the constant times the derivative of the composite function. Let's find that derivative using the chain rule. The outer function is something to the power of -1. The derivative is -1 times something to the power of -2. The inner function is ln x. Its derivative is 1 over x. So we multiply by 1 over x. Now we substitute this back into our expression for x. This gives us -ln 5 divided by x times the natural logarithm of x squared. This is the same result as the memo, just written slightly differently. Finally, let's explore differentiating some special trigonometric expressions. These examples are particularly elegant because they simplify to something very compact. Consider differentiating y equals ln of the quantity secant x plus tangent x. We have an outer function, ln, and an inner function, secant x plus tangent x. Let's apply the chain rule. The derivative is 1 over the inner function times the derivative of the inner function. We need to find the derivative of secant x plus tangent x. The derivative of secant x is secant x tangent x. The derivative of tangent x is secant squared x. So the derivative of the inner function is secant x tangent x plus secant squared x. Now let's substitute this back into our expression for dy by dx. We get 1 over the quantity secant x plus tangent x multiplied by the quantity secant x tangent x plus secant squared x. Notice that we can factor out a secant x from the second term in the numerator. This leaves us with secant x multiplied by the quantity tangent x plus secant x, all divided by the quantity secant x plus tangent x. The term in the parenthesis in the numerator is identical to the denominator. They cancel out perfectly, leaving us with a remarkably simple answer. The derivative of ln of secant x plus tangent x is just secant x. This is a very useful result to remember. Let's look at a similar trigonometric identity example. This time, we're differentiating y equals ln of the quantity cosecant x minus cotangent x. As before, we apply the chain rule. 1 over the inner function times the derivative of the inner function. This gives us dy dx equals 1 over the inner function, cosecant x minus cotangent x, times the derivative of that inner function. Next, we need the derivatives of cosecant x and cotangent x. The derivative of cosecant x is negative cosecant x cotangent x. And the derivative of negative cotangent x is cosecant squared x. Now we substitute this back into our chain rule expression. This gives us dy/dx equals the quantity cosecant squared x minus cosecant x cotangent x all over cosecant x minus cotangent x. Similar to the last example, we can simplify this by factoring the numerator. Factoring out a cosecant x from the numerator gives us cosecant x times the quantity cosecant x minus cotangent x, which is exactly the same as the denominator. The numerator and denominator cancel, and we are left with another simple result. The derivative of ln of cosecant x minus cotangent x is just cosecant x. Let's quickly recap what we've learned. The chain rule is a fundamental tool for differentiating composite functions. Functions of functions. The core idea is to differentiate the outer function, keeping the inner function as is, and then multiply by the derivative of the inner function. We saw that you can use a formal U substitution method, or, with practice, you can apply the rule directly, which is faster and more efficient. Both methods yield the same correct answer. Remember, the final answer should always be expressed in terms of the original variable, x. You now have a solid foundation for differentiating a wide range of complex functions using the chain rule. Keep practicing, and it will become second nature. Thank you for joining this tutorial. If you found it helpful, please consider subscribing to Math Zone African Motives for more videos like this. Practice is the key to mastering calculus.